Assalamualaikum. My name is Fauzia A. Marahom Salik from BECE 3 with SCED code 50059CE324, and I am the first reporter for this group. So the topic that was assigned for us was in module 4 entitled Travel Demand Forecasting Traffic Assignment. So the learning objectives of this lecture is for you and for us to determine the user equilibrium and system optimal solution to traffic assignment problems. Differentiate between the user equilibrium and system optimal solutions. So, traffic assignment. At this part, we are in the final step in traditional planning model. We are going to determine which routes will be used and how much traffic can be expected on each route. It requires the following data, which is the estimated number of the motor vehicle trips between zones, available routes between zones, and travel times on each route. Then, after that is the decision criteria by which users will select the routes. So, yung diagram po na nakikita nyo po dyan sa screen is tinutukoy niya kung paano sinusolve yung ratio proportion ng time travel over the time number turns. So, syempre, after mo malaman kung gaano siya katagal at kung gaano kataas, then at that point is magkakaroon na ng idea kung saan ba tayo dadaan or kung ano yung magiging solution natin when it comes na dumating yung traffic flow. So, meron tayong routes choice percent in a classic equilibrium problem. Mamaya, malalaman nyo sa susunod na report kung ano yung sabihin ng equilibrium, ng user equilibrium, pati yung optical. So, meron tayong 3 ways. At first is the route choice decision are in a function of travel times. So, sabi dito daw is kapag mas mataas yung route number, then mababawasan yung possibility ng mga travelers na ma-come up yun. Syempre, so the more na mahaba or longer, then the more na matatagalan silang makakarating sa destination nila. Check. So, number 2 is travel times are determined by traffic flow. So, syempre, malalaman natin kung gaano siya katagal, lalo na kapag nalaman mo kung gaano rin yung kalaki ng factors when it comes to traffic flow. Kasi traffic flow will serve as the friction or resistance na pag magpipigil sa travel times. Then lastly is the traffic flow is a product of route choice decision. So, syempre, pag nagkaroon ka ng traffic flow, then that's the time for the user to think which road might be perfect for her or to him para makarating sa destination nila. So, in short, syempre, ba't ka pa pupunta doon sa way na mas tatagal ka pa kung meron namang shortcut na makakarating ka doon sa destination mo. So, for the mathematical relationship between route travel times and route traffic flow is, syempre, as a whole, kailangan natin ng highway performance function. So, for the statistical or maybe formula kung paano isosolve yung iba't ibang ratios is madidiscuss po yan nung next reporter, which is si Kim Raida Gefar. Thank you!
Assalamualaikum and hi everyone, I am Kim Raida Gefar, the next reporter of this group next to Miss Marahom Salik. Let's move on to the capacity restraint method. So, capacity restraint method assigned traffic possible routes in an iterative manner. So, one of the examples is the BPR or Bureau of Public Roads. So, BPR functions relating to the travel time to the flow. So, let's take a look at the figure on the PowerPoint provided. Dito, mapapansin natin ang relations between the travel time and the vehicle volumes every day, for example. So, like, nagmamatter ba or does it matter yung flow ng travel versus the number of vehicles? So, probably, yes, and we will know that later on sa mga next reporter po.
We have an equation here of the VPR, which is T equals to T sub O or 0 times 1 plus 0.15 times V over C raised to 4, wherein T is our travel time, T sub O is the free flow travel time, V is the volume, and C is the capacity.
Under traffic assignment, we have road choice behavior. So, this road choice behavior is often modeled based upon Wardrop's principles. So, ano bang meron sa Wardrop's principles? So, si Wardrop po or John Glenn Wardrop ay isang mathematician and transport analyst. And na-develop niya ang first and second principle of equilibrium in the field of traffic assignment, which is yung dinidiscuss namin dito. Since ang traffic assignment or yung main topic dito, as what I have said, is a process in which ini-estimate natin ang volumes sa transportation system. Under route choice behavior naman, we have to analyze the two principles of Wardrop. So, una is ang first principle na nga.
In first principle, users choose the route that minimizes their own travel time.
So, our example in the first principle, which is the user equilibrium, it is a method that is most widely used. It is a user-driven traffic assignment in which user chooses the most convenient path selfishly. So, the keyword there is selfishly. So, kasi dito, pinipili ng user mismo ang most convenient na path for him or for her, guaranteed na fairness or may fairness na mangyayari among users.
For the second principle, users distribute themselves on the network in such a way that the average travel time for all users is minimized.
For the second principle, under dito ay ang system optimization. So, in this case, users would avoid congestion even if it results to higher travel time for themselves. So, if may dalawang road, let's say, wide road and small street, mas pipiliin ni user na dumaan sa small street kahit gaano ito kalayo para lang maiwasan ang pag-cause ng congestion doon sa wide road. So, ganun lang po ka-simple ang second principle of Wardrop's.
Going back to user equilibrium, when determining traveler road choice, two important assumptions are usually made. One is travelers will select a route on the basis of travel times, and the other one is travelers know the travel times that would be encountered on all available routes. So, given this information, the travel time between two zones on all used routes will be equal, and under user equilibrium, travelers cannot improve their travel times by unilaterally changing routes, which I have discussed already a while ago. So that's it, I guess, for my part. Thank you for listening and watching at the same time.
So, Assalamualaikum warahmatullahi wabarakatuh. My name is Nalati Mastura. So, I am the next reporter. User equilibrium example problem. Assuming user equilibrium condition, determine the following assuming an hourly flow rate of 4,500 vehicles per hour. So, we have the travel times on each route, traffic volumes on each route, and total system travel time. The highway performance function can be written as T1 is equal to 6 plus 4x sub 1, then T2 is equal to 4 plus x sub 2 raised to the power of 2, where T1 and T2 are the average travel times on route 1 and route 2 in minutes, and x sub 1 and x sub 2 is the traffic flow on routes in 1 and 2 in 1,000 seconds of vehicle per hour. The basic flow conservation identity is Q is equal to x sub 1 plus x sub 2 is equal to 4.5, where Q is the total traffic flow between the O to D pair in 1,000 seconds of vehicle per hour. If we assume all the traffic is assigned to Route 1, so we pull all 4,500 vehicles on Route 1, we find that 25 minutes travel time. Under that situation, people could obviously switch to Route 2 and improve their travel time. which is an indication that route 2 should be utilized similarly if we assigned all the traffic to route 2. That would result in 24.25 minutes travel time, and those travelers could easily switch to route 1. Then to improve that time. And from this, we can conclude that both routes will be used. Wardrop's user equilibrium definition gives T1 is equal to T2. So we have an equation here. 6 plus 4x sub 1 is equal to 4 plus x sub 2 raised to the power of 2. From flow conservation, x o sub 1 is equal to 4.5 minus x sub 2. So we have here the value of x sub 1. So we can substitute it to the equation, which is 6 plus 4 times 4.5 minus x sub 2 is equal to 4 plus x sub 2 raised to the power of 2. So the result here, we have the x sub 2 is equal to 2.899. At para naman makuha natin yung value ng x sub 1 is we need to substitute it to the equation, which is the x sub 1 is equal to 4.5 minus x sub 2. So, since meron na tayong value ng x sub 2 dito, which is the 2.899, we can substitute it. So, the answer for x sub 1 is 1.601. So, the value of x sub 1 and x sub 2, we can multiply it to 1,000. So, the answer is 2,899 vehicle per hour and 1,601 vehicle per hour, which gives average route travel times of T1 is equal to, so i-substitute lang natin sa equation. So in T1 is 6 plus 4 times the answer, yung nakuha natin na x sub 1, which is the 1.601 is equal to 12.4 minutes. Then ganun din sa T2, substitute the mga value na nakuha natin. So, T2 is equal to 4 plus 2.899 raised to the power of 2. So, the result is 12.4 minutes. So, as you can see, the T1 and T2, the result are the same. Then, lastly, in determining the total system travel time, lahat ng values na nakuha natin is we need to substitute it to this formula, which is S of x is equal to x sub 1 t sub 1 times x sub 1 plus x sub 2 times x t sub 2 times x sub 2. So the answer here is 930 vehicle hour.
Assalamualaikum warahmatullahi ta'ala wabarakatuhu. I am Nuraini Ibrahim from DSCE 3, the fourth reporter in chapter 12, lesson 4. So the assigned topic to me is the user equilibrium example problem. So the basic flow conservation identify is Q is equal to x sub 1, which is the first route, plus x sub 2, which is the second route, that equal to 4.5 or the 4,500 vehicle, where Q is the total traffic flow between the OD pair in 1,000 seconds of vehicle per hour. Check to see that both routes are used. So, kailangan nating malaman na ang dalawang ruta ay nagagamit because some strange solution that will include negative volume. For example, if we assume that all the traffic is in the route 1, we find 25 minutes travel time. So, ang mangyayari, ang mga tao ay magsiswitch sa route 2 dahil mayroon lamang itong travel time na 4 minutes. So, the route 2 will be utilized. Similarly, that we assign all the traffic sa route 2 naman, kung saan ito ay mayroong 24.5 minutes travel time, the traveler would easily switch to route 1 because it has a 6 minutes travel time. And from that, masasabi natin ang dalawang ruta ay nagamit or the both route is ultimately utilized. Wardrop's user equilibrium definition gives us all routes is being utilized, their travel time is equal to one another, which means T sub 1 is equal to T sub 2. So for this equation, which is 6 plus 4x sub 1 is equal to 4 plus x sub 2, is isa-substitute lang natin ito, which is itong x sub 1 sa 4.5 minus x sub 2. So, ang substitute na natin siya, ang x sub 2 natin, which is the second route, is mag-equal siya sa 2.899. Tapos, ang x sub 1 naman natin, which is yung first route naman, is mag-equal siya sa 1.601, which is, i-convert lang natin siya sa vehicle per hour, which is ang x sub 2 natin ay magiging 2,899 vehicle per hour, at ang x sub 1 naman natin ay magiging 1,601 vehicle per hour, which gives average route travel times of, so i-substitute naman natin siya sa t sub 1, which is equal to 12.4 minutes, and sa t sub 2 naman, substitute lang natin, which is magre-result siya sa 12.4 minutes. So, ang ibig sabihin nun, is equal to one another.
Hi, I'm your next reporter, Narjeline Fajardo Limanay, and for today's video, I am going to discuss to you the system optimization. So in contrast to user equilibrium under system optimal solution, we find that there were likely a single route strategy that will minimize the total travel time across a system, but that's not necessarily going to correspond to our user equilibrium case. So, stated mathematically, we can return to our total system travel time function that was presented in the previous slides. We have a number of different routes, each with their unique volumes and travel times. And if we simply pick that function and minimize that, that will then deliver us a system optimal solution, and so on know volumes and travel times each of those respective routes. And so we'll returning the prior example problem and calculate those exact same quality of the travel time, traffic volumes, and the total system travel time. So previously, we had determined what the performance functions were for each of these roadways. And so the system travel time is simply equal to the volume times the respective travel times function. And so just extending this expression, we end up with a quantity that we see right here. So we have one equation and two unknowns. And so the question is how do we solve for x sub 1 and x sub 2? And we return once again to conservation of flow. And since we know that x sub 1 plus x sub 2 is equals to 4,500 vehicles per hour, we can simply solve in for x is equals to 4.5 minus x sub 2 quantity. And we'll then end up with this equation that you see demonstrated right here. And this is an equation for our total system travel time as a function of the volume on the second route. And that's all. Thank you.
Assalamualaikum everyone, I am Fazal Ramaliga, and this is the last part of our report, which is about the traffic demand forecasting, traffic assignment. So in this system optimization, the total travel time is denoted as the summation of xn times t quantity xn. So in this case, there are two systems, so x1 times t1 times x1 plus x2 times t2 times x2. So the result are given are this. So 233 vehicle times 14.13 minutes. Then the other system, which is the 2,467 vehicle times the time, which is the 10.08 minute, with a total of 893.2 vehicle per hour in an hour. Under this EU, the total travel time is approximately 930 vehicle hour. So the system optimization solution result in a system-wide travel time saving of 36.8 vehicle hour. So by those data, we can now generate the 4-step travel demand model, which is composed of 3 parts or 4 parts, which is the trip generation, then after trip generation go to trip distribution, then the mode of choice, then the traffic assignment. So under the trip generation is the trip production, which is from zone 1 you have data PI, then zone 2, zone 3 you have data. Then in trip attraction, from zone 1 you have attraction 1, then 2, 3 you have attraction. Then using that data we can now go to the trip distribution. So this is the tabulation of the two data, so the trip distribution. Then after summing it up, we are now going to the mode of choice. So you will choose mode 1 and mode 2. And after that, you are to, the last part is the traffic assignment. So the route, you will come up with 3 routes, or it depends on your data, or it depends on the zone you are considering. So since we are considering 3 zones, so which means that we have 3 routes. So the traffic assignment will be distributed. So route A, route B, and route C. So that's how the travel demand model goes. So that would be all. Thank you for listening.